Okay, before viewing this video, you should know a little bit about inheritance, either through the first lecture on inheritance or by reading the information in your textbook. In this example, I'm going to go through a clock class, and we're going to progressively go through the inherited process all the way to the more complex inherited process, which will allow us to achieve polymorphism. Okay, so the first thing we'll look at is a simple clock class. This clock class is using a time class, not our time class, but it gives us the time for the computer that we're on. All right, so in our clock class, we have a constructor here. Notice it's a constructor that's just accepting a parameter of a military Boolean value that's going to allow us to show the clock, the time in military time or standard AM PM time. We have a get location function. Right now that get location function is very generic. It's just going to say local, so wherever we are, that's the local time. Get hours, get minutes, and is military is a function that's going to allow us to say whether or not we should show this time as a military time. So if we look at the actual functions, again, the constructor just initializes the Boolean value passed to it during instantiation. So if we instantiated clock 1 with true, that time is going to be shown as a military time. Get location just simply says local. Get hours uses this time class that's not our time class, but in effect, it returns the hour from the computer that we're on. Now, when we take that hour, if it's a military time, we're simply going to return that hours as it is. But if it's not a military time, we have a little algorithm here to change this thing into a AM PM time, 5 a.m. or 5 p.m. Get minutes simply returns the minutes, and then finally is military lets us know whether or not this is a military time that we should be displaying. Here is the actual client program that instantiates two clocks. For the first clock, it's going to be a military time. We're going to show the hours and the minutes. And for the second clock, it's going to be an AM PM time. We're going to show the hours and the minutes. And then we're asking the user if you want to see the time again. So for the sake of this demonstration, we have already executed this program. And we see that the military time is 15:03 and the AM PM time is 3:03. We hit yes to show the time again, and now it's 3:04. And that is the clock class, a very simple class, but we're going to take this class and build upon it. Okay, so now for our second example, we see that we still have our basic simple clock class, but now we have taken the clock class and we're going to derive a new class called the travel clock class. So in this example, we call the clock class the base class or the parent class, and the travel clock class the derived class or the child class. Basically what this means is that the travel clock is going to be a clock and more. We achieve this by giving it the inherited syntax right here. So I'll talk about this syntax, but notice throughout the program I have bold-faced everything that's important to this topic, right? So in the lecture we talked about there being three types of inheritance: public inheritance, protected inheritance, or private inheritance. In this case we have public inheritance. Each successive inheritance gets a little more restrictive. In our case of public inheritance, we say that we inherit all of the public and protected sections from the base class, which in this case is the clock class. So the inheritance is taking place by giving this notation. The travel clock is a clock and more. So all the things are inherited over here. Now, when we say inherited, when we look at public functions or any functions in the base class, there are three ways this can go. The first thing that could happen is a class could simply just say, I want to inherit the base class function directly and I'm not going to do anything to it. So in this case, get minutes does not appear over here, so get minutes is inherited by the travel clock class. If a travel clock object invokes the get minutes function, it will be invoking this function in the base class. The second thing we can do is replace the function altogether. In this case, get location is over here in the base class, but it's also over here in the derived class. Now, when we have a function with the same signature in both classes, we are saying that the derived class is redefining that function. So that's a term for you, redefining the function. Get location has been redefined. In fact, get location has been replaced altogether. If you look at get location in the base class, it is just simply going to return a generic local for the time, the location that we are at. But if we look at get location in the derived class, it's actually going to return a location that is a string indicating where this clock is telling the time for. So in this example, we have Rome and Tokyo as being the locations. So the travel clock is not just going to say it's local, it's going to say it's the time in Rome or the time in Tokyo. So this function has completely replaced the base class function. And then the third scenario is the derived class function can do what the base class function is doing and more. We call this extending the function. So both of these have been redefined. This one redefined, get location redefined and replaced. And this one redefined and extended. What do we mean by that? If we look at the get hours function here for the derived class, the get hours function is first going to call on the clock get hours function. So it's going to do everything that the get hours function in the base class does, and then it's going to come over here and do more. So if you see here, in order for us to call this get hours from the clock class, we have to qualify by giving the name of the class and the binary scope resolution operator. This tells the code to call on the clock's get hours and not our own. If we didn't have this here, this would result in a recursive call and really an infinite loop, because this would now tell the code would now be saying to call on your own get hours. So we would be caught in a recursive loop calling ourselves over and over again. By qualifying it, we call on the get hours, it gets the hours, returns it, and then if it's a military, it figures out the time difference, and if it's a standard time, it figures out the time difference. So now we have created a new class that's using some of this stuff over here. We're using get minutes, we're using his military, right there, we're using his military, we're using get hours, and we then have some different stuff going on our own. So we say the travel clock is a clock and more. Now let's take a look at the client code. So now we have instantiated three objects, one of the base class, clock 1, and two of the derived class, travel clock 2 and travel clock 3. Travel clock 2 is going to show a military time for Rome, a 9 hours different. Travel clock 3 is showing a AM PM time for Tokyo, a -7 hours different. So when we run this, we're simply going to print out these 3 times in succession. And again, if we look at the execution of this, we see that it says local time and then Rome time and Tokyo time. Now let me point out, because the travel clock is a clock and more, travel clock 2 and travel clock 3 still has access to all the base class functions. So for instance, if I use the scope resolution operator with this clock 2, instead of getting the location Rome here, I can ask to call on the base class get location, and it's simply going to show the local time. So I'll run that real quickly. So I see here that now, although I'm in Rome, I still have it saying that it's the local time. And the reason it's saying it's the local time is because I've changed this call right here to say I don't want to call the derived class get location function. I want to go directly to the base class get location. So I qualified it right there to say, give me that one. In other words, what I'm trying to point out is that all of these functions are available from the derived and the base class. Okay, so let's go back for a minute and review some of these properties. First of all, we had this clock class, and of the clock class, we set it up where get minutes is military, and military is going to be inherited directly by the travel clock class. So this right here illustrates what the clock class looks like. And what I'm trying to show right here is what the travel class clock looks like. So I don't like the fact that this changes colors right here, but I do want to illustrate that this is the derived part of it, but really this is all just one big object. So if I could blur the lines here or shake it up, I want you to see that all of these functions belong to the travel clock class. So everything that's in here, the military data, the location, the time difference, all a part of this big object. Again, the color is just to show you the difference between the derived class part of it and the clock part of it. But if you remove that color scheme, you'll see that this is all just one big object. In other words, the clock, travel clock, is a clock with more, okay? So of this, you see that I have a get location in the clock class and a get location in the travel clock class. So the base class and the derived class. I, in the last demonstration, showed you that I can call on the get location from the base class directly. And if I don't use that scope resolution operator and I have a derived class object, it's going to give me the get location for the derived class. Then we talked about three things that could happen to functions within the derived class. But before we talk about that, one thing that I failed to mention is that this travel clock class constructor is actually going to be preempted and call on the base class clock constructor by using something called the member initializer. Now in this case, to use the member initializer, it's a colon right outside the class header before the curly brace, and it's the name of the class and any parameter that you're going to pass to the class. So what happens is when we instantiate a travel clock object, it's going to call on its constructor, preempt itself, stop right there, call on the base class constructor to fill in this military time, and then once that executes, it's going to return back and do the constructor for its part. So if you want to think about it, it's going to build the base class part of it first with this call to that constructor, and then come back and build the derived class part of it. All right, so now to the three scenarios. The first scenario again is I take a base class function and I simply replace it all together. So I write a new function that does something different from what the base class function is doing. I'm replacing it. The second scenario is to extend it. So to extend it here's the base class get hours, here's the derived class get hours. Notice the base class get hours is being called right here by using the scope resolution operator in the class. I'm going to call on this, do this part, and then do more. So I'm extending what the hours function is actually doing in the derived class. And I didn't mention the other scenario is that you just inherit the functions directly, like is military. So these are inherited and nothing is being done to it. This can all be reviewed in this section right here, where I talk about the three things that you can do to a base class function. You can inherit it, which means you don't do anything, replace it or extend it. And I give you some scenarios on that, okay? That leads into what happens when we are using these objects with pointers. Therein lies some different scenarios. So let's talk about that a little bit. Hey, first, this is my very, very crude drawing of what would happen if you had a base class pointer, a derived class pointer, a base class object, whether it be dynamic or static, and a derived class object, whether it be dynamic or static. Again, I illustrate a derived class object by saying it's a base class object with a little more on it. So I draw that little hook right there to let you see that the derived class object is the base class object and more. So what happens? Well, we have really 6 scenarios right here. Let's go through all of them. The first scenario is, what happens if we try to set, told you it's really crude, if we try to set the base class object equal to the derived class object. So we're trying to assign the base class object to a derived class object. So we have a clock, and we want to take the time from a travel clock and assign it to a new clock. What happens? Well, if you can imagine this being a bucket right here, if we pick this thing up and try to drag it and drop it in here, all of this will fit in here, and this part right here will be cut off. We call that slicing. So if I have a derived class object that I assign into a base class object, the base class part will be copied, the derived class part of it will be sliced off. This is called slicing. So that's valid. We can do that. Now the alternative, again, we always do our assignment statements left to right, but for the sake of this argument, what happens if we try to take a base class object and copy it into a derived class object? Well, we take this base class object and put it into this bucket, and we see that it's not enough to fill the entire bucket. All of this will be filled, but this will go undefined, not initialized to any values. The computer doesn't want to see that, so it will warn you and tell you that this is an error. Copying the base class object into the derived class object is a no-no when you're doing it straightforward, okay? In this case right here, it's invalid because we don't initialize or fill all the values. Remember, over here you have time difference and location, and it's not going to get a value because this object doesn't have a time difference in location. So, strike 1, that's not valid. What about taking a base class pointer and assigning it to a base class object? Well, of course, that would be completely valid, right? Now this base class pointer can refer to any of these functions in here by simply going base class arrow get base class arrow get hours. Okay, so that would be a valid call to a base class function. All right, so that's valid. What about taking a derived class pointer and pointing it to a derived class object? Again, this is valid because then, again, we could say derived class arrow get location, and it will get the location of the derived class object. So both of those are valid. Now, here's where we get into maybe a little complication. What if we take a base class pointer and point it to a derived class object, as in here, base class pointer points to a derived class object. This, in fact, is valid, but understand what's going on here. The base class pointer can only see the base class part of this object and cannot see the derived class part of it. So when a base class pointer points to a derived class object, by default, it only sees the base class part of that object. All right? And then finally, what happens if we take a derived class pointer and point it to a base class object. The derived class pointer pointing to a base class object is going to have problems again, because the derived class pointer wants to see that derived class part of it that's not there. So time difference, location is not there for that derived class pointer. Again, you would get complaints from the compiler that the derived class pointer can't point to this base class object. All right. So the moral of the story is base class pointers can point to both base class objects and derived class objects. But by default, base class pointers can only see the base class part of each one of these objects and not the derived class part of it. If we scroll down here, I'm about to show you a scenario where we have an array of pointers pointing to both base class objects and derived class objects, and we'll see what happens. Okay, so let's look at our third example. In our third example, we have an array of pointers. So in particular, 3 pointers that look like this. Again, my crude writing, I'm just learning how to use this little pen. So the first one is a base class, and the other 2 are derived class objects, okay? So I fill them with these dynamic objects, the first being the base, the second 2 being the derived class. But these pointers are of type what? They're of type clock, so they are base class pointers and should only see the base class part of these 2 travel clock objects. Even though they're dynamic, they're still, again, derived class objects that have a base class part to it, okay? So I'm just simply going to go through a simple for loop looking at each one of these. So the first time through, I'm looking at clock sub 0, then clock sub 1, clock sub 2. All right. So when we run that, we get something that looks like this. And again, I'm just seeing local time, local time, local time. Yes, the last one is printed not in the military time, but the standard time. But nevertheless, when my base class pointers looked at that derived class object, it only saw the base class part of it. Well, this is not really that good. So what can we do? Okay, so how do we solve that problem? Here we're looking at the third example of the clock and travel clock class. Notice now that the get location and get hours functions are now preceded by the word virtual. By putting the word virtual in front of these functions, by the way, once you put the word virtual in front of the function in the base class, it propagates to the derived class. So you don't have to put virtual in front of the function prototype in the derived class. It's automatically virtual. I recommend putting virtual in front of the derived class prototypes also, because if the travel clock class gets inherited by another class, it needs to know that these functions are virtual functions. So what does that mean to be a virtual function? Well, when we say a virtual function, we mean that the function is really not there until it's needed. Okay, so let's go back to my crude illustration again. When we think about function calls to a class, we think of something called binding the function. Binding the function just means to take the call to the function and bind it to a certain set of code that it will call when the computer starts to execute the code. So in this case, we have static binding. Static binding is done during compile time. In other words, what we're saying here is if I make a call to bObject.getLocation, I know that I'm calling the base class getLocation because this is a base class object. If I make a call to invoke the get location with a derived class object, D object, I know that I'm calling the derived class get location. Remember in the last example I showed you, if I wanted to call the base class one, I would put the scope resolution operator and put that on there. But again, the compiler would see that notation and know that it should call on the base class get location. All right. So during compile time, by just looking at these two sets of code, I know exactly which function to call. The compiler would then place a call to that function in place of this syntax right here. So it basically would say, and I'm just giving an example, call jump to memory location C7 and start to execute that code for the base class get location. Or jump to memory location D3 and start to execute that those instructions for the get location for the derived class. Now, that's static binding done during compile time. The problem is with pointers, we said that pointers can point to base class objects or derived class objects. Now, if I didn't have that virtual function, again, these calls would be very simple. I would simply jump to the base class function right here and the derived class function right here. But as soon as I introduce a virtual function, I'm telling the compiler, don't figure out which function I should call yet. Let that be a virtual call that will happen dynamically during the execution of the program. So during the execution of the program, the compiler or when the program is executing, it will look and say, what is that base class pointer pointing to? If it's pointing to a base class object, then I'm going to bind it dynamically to the base class function. If it's pointing to a derived class object, then I'm going to bind it dynamically to a derived class function. Dynamic binding is also sometimes referred to as late binding, and static binding is sometimes referred to as early binding. Early binding because I'm binding it during compile time, and late binding because I'm binding it during the execution of the program. Now, for the sake of this class, we're going to say we can always identify dynamic binding when it deals with pointers, right, and virtual functions. But there is a scenario when we're passing objects through a function parameter list that late binding can also take place, especially when we're passing by reference, right? So let's keep that in mind, but for the sake of this class, we'll say the dynamic binding will always have this notation. So you're probably asking, why do I have D pointer location? Don't I know that that should bind to a derived class? Well, the derived class could be inherited by another class, and if that's the case, we need to dynamically or late bind that call also. So if we get back to the code, by having these functions with the word virtual in front of it, what we're saying here is when we call get location, first check to see what kind of object we're looking at. If we're looking at a base class object, then bind it to the base class get location function. If we're looking at a derived class object, then bind it to the derived class get location function. And as we run this code, we see now that the local time here is in fact the base class object, but the derived class ones actually went through and picked out the derived class functions. We refer to this as polymorphism. Polymorphism simply means this, that when the base class pointer looks at a particular object, that object, when using virtual functions, will morph into what it actually is. So that base class pointer points at it and says, you're a clock, and that object morphs and changes and says, no, I'm not a clock, I'm a travel clock. So if you take the word polymorphism and break it down, it means what? Many changes. So a pointer that's pointing, in class we talked about this, a pointer that's pointing to a shape, that shape will now say, I'm not a shape, I'm a triangle. I'm not a shape, I'm a square. I'm not a shape, I'm a rectangle. So that shape pointer can point to many different objects, and that object can convey what it is during execution time by making the function virtual and figuring it out. So just to try to clarify that again, when I make a call here to get location, this is not going to be bound until the function executes, and the computer is going to say, hey, that is a travel clock. Let's call the get location for the derived class travel clock class. All right. Okay, so we've kind of established what polymorphism is. Polymorphism is the ability for the base class pointer to point to a derived class object and see it as a derived class object instead of just the base class object. Without polymorphism, if we take a base class pointer and point it to a derived class object, that pointer would only see the base class part of it. With virtual functions, we achieve polymorphism by letting that base class pointer resolve the call or the binding to the function during execution. We're saying that function is virtual, figure it out while the program is running. Okay, so now that we know what polymorphism is, let's take it one step further. In this example, we have virtual functions again, get location and get hours. But for this get location, we have a little notation here with an equals 0 behind it. The equals 0 behind it simply tells the computer or the compiler that this is what we call a pure virtual function. And what's the implications of a pure virtual function? A pure virtual function changes a base class into what we call an abstract base class. We call that an ABC, an abstract base class. So as soon as we put that equals 0 in any of the functions, again, any of the virtual functions, it becomes an abstract base class. This could be one pure virtual function or several. Once you put it in one, it's done. What's the implications of an abstract base class? It simply tells the compiler that let's try to compile this program and see what happens. So it's trying to compile it, and yes, it came up with an error. It says object of abstract class type clock is not allowed. Clock cannot instantiate abstract class. All right. Once a base class becomes an abstract base class by creating one pure virtual function, we're telling the compiler we will never instantiate an object of that class. And that kind of makes sense because earlier we talked about the mammal class being the base class for derived class mammals, dogs, dolphins, bats, bears. Well, if you think about it, there are no mammals. There are dogs, cats, dolphins, and bears. So we don't need to create any mammal object. Mammals don't exist. They're either dog, cats, dolphins, or bears. We'll talk about the appliance class. An appliance could be a refrigerator, a VCR, a microwave. Again, we don't need to instantiate any appliances. We need to instantiate microwaves, refrigerator, washing machines. Maybe we have a repair shop. On that list, that linked list of repairs, we would put washing machines, refrigerators, toaster ovens, but we will not put any appliances. There are no appliances. There are specific things. What's nice about this, though? This abstract base class will allow us to create a pointer that will allow us to link all of those objects together. So we can link the circles with the rectangles with the triangles by using an abstract base class called a shape.